Dr. Abdessatar Souissi. So, Dr. Abdessatar Souissi earned his agrégation de mathématiques in 2012. So, from 2012 to 2018, he taught as the professor agrégé at IPEST, Carthage University, Tunisia. In 2017, he completed his PhD at the Faculty of Science of Tunisia, focusing in quantum Markov chain in KD3 and under the supervision of Professor Abdessatar Barhoumi and co-supervised by Professor Farouk Marhamidov and Professor Luigi Accardi. Since 2018, he has been an assistant professor and later an associate professor at Qassim University, Saudi Arabia. His research mainly explored in one-dimensional quantum Markov chain and their ergodic property, quantum Markov chain in tree, particularly in connection with phase transition in Pauli type models and the quantum information. Additionally, he has recently been investigating Haydn Markovian and non-Markovian model and their application. He's also delved into the foundation of quantum Markov field in graph. So the talk of Dr. Abdessatar Souissi entitled Haydn process and Haydn Markov process in the classical and quantum case. So, Dr. Abdessatar, we can start now.
Thank you very much, Mohammed. I would like to thank Rafiq for the invitation and all the team of the Applied Mathematics webinar for this great occasion to speak to audience with several cultural knowledge. So today I'll be talking about Haydn processes and Haydn Markov processes, classical and quantum. Here we can see that there are two parts. The Haydn processes, both Markovian and non-Markovian, also they are classical and quantum. So the word classical refers to classical probability, quantum to quantum probability, and this is from classical mechanics and quantum mechanics. That's why we see classical and it's related to the classical statistical mechanics and quantum. Okay, I will start with first. This work is joined with Professor Accardi, Dr. Souissi, and Prof. Yang. So I will start with small motivation. The Markov models are known to be statistical models with fruitful applications in a wide range of domains, including physics, machine learning, namely natural language processing, and also computer vision and so on, and also in speech recognition, in bioinformatics, in finance as well. So it's quite natural to be motivated with these applications in several domains to investigate the quantum counterpart, namely with the growth of the quantum technology, such as the quantum machine learning, quantum computing, and so on. So it's quite natural to focus that a quantum version, which is like sufficiently satisfactory, will play a crucial role in terms of application. So first, what is a Haydn Markov model? From a probability viewpoint, it's a pair of stochastic processes, Xn and Yn, where Xn is a Markov chain, which is not observable, but rather hidden. I mean, the transitions are hidden. And it's known that Markov chain are stochastic processes having this numerous property that says that the future of the process, given its present state at time n and its past, depends only upon the present state. And this weak dependence allow to modelize many phenomena. Now there is also an observation process which satisfies this conditional independence assumption that says that at time n, Yn, the observation depends only upon the hidden state at the same time. So it does not depend on the. Now we have.
Sorry to interrupt. This is O or 0?
Yes.
YL equal 0 or O?
It's O.
O, okay.
It's O
What is O?
related to the observation, you know,
Okay.
like because the observation. Yeah, the observation are denoted by O in general, or we may say any other symbol.
Okay, thank you.
Okay, it's not zeros.
Okay.
Okay. Now, as we can see, each observation depends only upon the same time hidden variable. I mean hidden state. Therefore, I mean it allows to extend the applications of Markov chains themselves to other processes for which the output is not necessarily Markovian, but it is behind that there is a Markov process controlling the transitions. Okay. Now we want to go to the next. I don't know. I don't know. I just want to know how to go. Okay, now it works. Okay, now for the couple of random variables, xn and yn, we have the distribution, which is defined to be a triple pi zero, a sequence of transition matrices Tn and the sequence of emission matrices Qn. And here the transition matrices are stochastic matrices, which control the transition of Markov chain, and pi zero is the natural state of x0. I mean the distribution of the variable x0, and Qn is called emission probabilities that encodes the transition of the observation of process yn in terms of the header process. Here explicitly we have pi n ij is this probability, so one can see that pi ij is positive and that the sum of pi nij equals 1, so that is a square stochastic matrix. The same for Q. However, Q is not necessarily a square stochastic matrix, it's rather a rectangular stochastic matrix. And formally, you can write the joint distribution of x and y to be the product pi x0 times the transition of the Markov chain Pn, Xn, Yn, and then we have the transition of the observation in terms of hidden states. Here, T, of course, is the number. Let's take an example. I would like to write first some notes. Okay. Now, by taking this example, we will illustrate, hidden Markov model through this example. For example, here, the transition in the state space of the Markov chain, let's take this probability to be 0.5. This one should be also 0.5. And here, for example, 1 out of 4. This one should be 3/4. And so on. Here also, for example, we take this transition to be 0, and so on. At the end, we will get a matrix P, which is stochastic and 4/4. The first line is the conditional probabilities given the state S1. It will be the probability of S1 given S1, which is 1/2. Then the probability of the transition from S1 to S2 given the initial state is in an S1, so it's going to be also 1/2, and so on. So it will be a 4x4 matrix. And now the observation will be encoded by a matrix Q, which gives the probability of OK given SI. For example, we may take P of O1 given S1, O2 given S1. It's going to be, for example, 0, 1, and for example, 0.9. So the first line will be 0.1 and 0.9, and so on. We have given S2, given S3, given S4. So it's a 4x2 stochastic matrix. These two matrices control the distribution of this Markov chain, which is in this case homogeneous in time. Now our purpose is not to study these basic things, but rather to extend them to a more general framework, which is the algebraic framework. Okay, concerning the algebraic hidden process, it requires an algebraic formulation of these processes. So we need to go from probability, I mean classical probability or probability theory, into operator algebras. And this should be in a smooth way, like it should not be a jump. Therefore, we just need to make some motivations for this transition, why we should go to an algebraic formulation of classical Markov chains and classical hidden Markov model. Simply because when we take a random variable on a probability space omega fp into a measurable space sp, so sp here is the sample state of x, and we extend the distribution of x. We know that the distribution in a given even a is the integral of the indicator of a dpx. If we extend this to bounded linear maps, it becomes a linear functional on this space. Now, if we see from a structural viewpoint, we remark that this space has a structure which is C-star algebra, and this map is a positive linear functional. Therefore, it's natural to think about extending this notation to non-commutative C-star algebras. Okay, this can coincide simply with the non-commutative measure theory. Therefore, we need to keep the characteristics of probability, which makes the difference between probability theory and measure theory, which are conditional expectation, independence, and dependence. Therefore, it should be an extension of these three notions to the quantum case. Okay, first I will give some. Yeah.
Sorry, in the slide before.
Yes.
Okay. In the last integral, this integral, it is small x and not capital X. This is f of small x and not capital X. Okay.
Yes, for sure,
okay.
yes.
Okay.
Because small x is the realization of.
Yes.
Indeed, it's. Yeah, it's just the realization of it.
Okay.
Yes. Okay. And thank you for this remark. Yes, it should be small x, otherwise it doesn't. Okay, now I will just introduce some basic notions about, indeed, only the definition. What is a C-star algebra? So it's an algebra over the field C, and contains a map called involution, satisfying these three properties. It's an involution indeed, because if we apply it twice, it goes to the identity. So its square is identity. And then A B star is B star A star. Alpha A plus beta B star is the complex conjugate of alpha times A star plus the complex conjugate of beta times B star. Okay, one can see these properties are satisfied by the transposate conjugate, the conjugate transpose in in MD of C or in B of H for H a complex Hilbert space. Therefore, one of the famous C-star algebras are the set of D by D matrices over C, or equivalently B of H for H is a Hilbert space over C. Okay. Also, when we are here is the notion of star algebra without topology. If you want to add the topology, we add the norm, which is called the C-star norm satisfying this property, which is a norm over the algebra satisfying this property. And here we are not really interested in the topological aspects of C-star algebras. And people who are interested in C-star algebra, they may, I will send some references, like some famous books in this direction, namely by Takasaki. Also, there is a book by Sakai and one by Bradley Robertson. There are many, many other books which are quite, I mean, they expose this theory in a very detailed way. Okay, now what we are interested on are linear functional, which are basically positive. I mean, what is a positive element in general in C-star algebra is an element that can be written as star A for central A, and identity preserving, which preserves the identity of B, and then in this case we call it state. Now we can formulate the stochastic processes in algebraic way. So as the C-star algebra L infinity, we take the tensor product of these C-star algebras, which are commutative, and then the distribution, I mean the joint distribution over a finite set F can be considered to be a state on this algebra, which is the tensor product over F of L infinity of Sn. And okay, here is a formal definition for algebraic formulation of a classical stochastic process. The same thing. We just reproduce the notion of a stochastic process in terms of states over commutative C-star algebra. So we are in the classical case here. I mean, in the usual probabilistic framework. Okay. Now, okay, using these properties, we can use this expectation to rewrite the Markov property. A Markov chain is a process having this property, the conditional expectation of any bounded map, bounded measurable map applied to the xn plus 1, given the sigma algebra generated by x0 till xn is the same as E xn given xn plus 1, g of xn plus 1 given the sigma algebra generated by xn. This is exactly what we obtain if we consider this state for a Markov chain. Okay, so little by little things merge from probabilities to functional space or algebras. And now we have this theorem, which is basically translate the correlation functions or the distribution of a Markov chain in an algebraic way. Basically, what controls the transition in a Markov chain is a Markov operator, which gives a similar expression of the joint expectation of the nth component of the Markov chain. And now the limit of this sequence, which is P0n, is like the full distribution of the Markov chain. This is well known, and it's just written in an algebraic. Okay, now to go further, we should investigate the quantum analog of the hidden Markov model. First, for the hidden Markov model, we have two processes: the hidden one and the observation one. For the hidden one, we take BH, which is L infinity C of SH, the commutative, over the sample space of the hidden random variables xn, which consist of Markov chain, and BON to be L infinity of SON, like the sample space of yn, the states yn. Okay, now we consider the algebraic tensor product of BHN, which is known to be quasi-local algebra, to be the usual tensor product of the commutative C-star algebras. Also, for the sample algebra of observation, we take AO to be the tensor product of BON. Now, for the HO simple algebra, it's quite natural to consider the tensor product of HO and H and AO to be like the sample space. It's like exactly the algebraic analog of the product probability space of the two processes Xn and Yn. Okay, now the joint distribution is defined to be a state over the algebra HO, whose correlations are controlled by this operator PH, which encodes the transition over the hidden algebra, it means of the hidden Markov process, and the observation, which is the restriction of PHO, I mean the marginal distribution in a probability language of the distribution PHO over the observation algebra. Till now, we have two components. We have the observation and the hidden. And now what's interesting is that in the classical case, which is this case, we can get PHO from the hidden and the observation with a dependency between them. We know that a conditional independence assumption that gives the correlation of the observation given the hidden. Now we arrive to a formal definition of what is a stochastic, a hidden process or hidden Markov process, because in the literature, hidden Markov models are introduced to be statistical models, because most of the people investigating hidden Markov models, they take them as a statistical model, and they are rather interested in applications of this model for several purposes. And what's really strange is that Markov chain have been heavily investigated in the literature, but hidden Markov model, only few papers, even there is no foundation of hidden Markov model in terms of as like famous stochastic process to the best of my knowledge. Okay, now we take this algebraic stochastic process as it's been introduced before, AHO, which is the HO simple algebra, the HO the joint distribution, and here are the sample at time n. It is called hidden process, it's not necessarily Markovian, if the H process, the O process is conditional independence of the H process. It means it satisfies this equation 10. It means each observation depends only on the associated hidden observation. Till now, we didn't involve the Markov property. We just defined a general notion of hidden process. Now it is Markovian if its hidden process is Markovian in the sense I explained before. Therefore, we have two definitions. One is more general for hidden processes, Markovian and non-Markovian. And the particular case is the hidden Markov process, in which the H process is Markovian. And we get this result that describes the correlations of a hidden Markov process in terms of what is called the hidden distribution, the distribution pH of the H process, and the emission operator. If you remember, we introduced it before a 4x4 stochastic matrix, and like a 2x4 in that example. Indeed, pH, which is the Markov operator, it extends that transition matrices of the hidden Markov chain. And BOH extend the emission matrix QOH. Q that is defined in that example to be 4 times 2 matrix. And now we can define it as an operator which is positive, like having that properties defined by that integral formulation. And what's really interesting is that PHO is simply a state on the star algebra AH. Now, everything is ready to extend this notion to non-commutative case. Before that, we showed an auxiliary result, which I see that there are a lot of notations, but I want just to summarize, because I know many people that are not familiar with these notations. Okay, in this section, we just proved that a Heda-Markov model, in the sense of this definition, is the restriction on an appropriate algebra of a Markov process in the H tensor O. I mean the direct tensor product of the two algebras. I mean the direct, we get like a result only on the commutative case. We have this. Like even an algebraic Heda-Markov model is the restriction of a Markov model, I mean a Markov chain on the full algebra, which is AHO. I mean AH tensor. And here are the correlations of this Markov chain. I mean the ingredient of the Heda-Markov processes are defined to be H tensor OA, HN minus 1, to be like the dimension of work. Now, to extend the notion of Heda-Markov model from the algebraic, the commutative case or the probabilistic case to the non-commutative case or the quantum case, we need like quantum conditional expectation, because they are key notion in probability, and indeed they make the difference between probability and general measure theory. Therefore, we should like have a convenient extension of this notion to the quantum case or to the algebraic case. Now we need the notion of complete positivity, because in the non-commutative case, the point is that the tensor product of two positive maps is not necessarily a positive one. Therefore, we need a stronger condition, which is given by what is called completely positive map. Here is a definition which says basically that the map P tensor the identity over MD is positive for each n. I mean, the map P tensor the identity over Mn is positive for every n. Okay. The first quantum extension of the notion of conditional expectation have been introduced by the Japanese mathematician Yamagaki in 1956 to be exactly the quantum translation of conditional expectation, which is a normal projection from a C-star algebra A into a sub-C-star algebra A, preserving the identity and so on, having the same properties. Here are the properties like which are like in general satisfied by classical conditional expectation. But this conditional expectation play a crucial role in the framework of von Neumann algebras, and it has a lot of applications. But to define the Markov property, we rather need a different notion, which is given by Accardi. And I'm sorry, there is an extra night, so it should be many century later. Okay, it's 1974. To be a quasi-conditional expectation with respect to a tricle rather than two algebras, we need a third algebra, which is C. And that Martingale condition should be satisfied with respect to the algebra C, not the algebra B. Because it turns out that if we consider the algebra C to be equal to B, this Markov property will be trivial. Because in the most important case, I mean, for us, we are rather interested by the CCR case, which is the canonical commutation relations algebras, which are the infinite tensor product of matrix algebras or general C-star algebras. Therefore, if we take simply a full matrix algebra, we know that the commutant will be, I mean, of B. I mean, this will be trivial in some way, because wait, here I should. I'm sorry, there is like a typo here, because here it's not right. Here it's like C the commutant of C intersect B. Okay. I'm sorry for this. Okay. Now, why for Oyamagaki conditional expectation this is trivial? Simply because if we take a full matrix algebra, for example, we take A to be MD tensor MP, and like B is MD, then the commutant of B in A is like this component, which is, I mean, MD tensor 1 here, tensor the identity. And the commutant of B, since B is a factor, therefore its center is reduced to the identity, then we take the second component, and therefore the intersection of B and its commutant will be reduced to the trivial C-star algebra, which is C times the identity. Therefore, it's useless to consider such a Markov property. Here, we have this property for C-star algebra, basically, which is not equal to B. Otherwise, we will not get any Markovianity in this sense. Another important thing is that here is written in the right way, you see? Okay. Now, these maps are known to be conditional expectation, and they encode the transition from the full algebra A into the algebra B, and the information is summarized in the. Why is it called Markovian? Because in general, we take this algebra to be the past. For example, C is, let's say, the C-star algebra generated by A0 till n minus 1. And like tensor the algebra Bn, I mean, let's say, I'm sorry here. Like, we can take C to be the algebra, the past algebra, 0 to n minus 1. And B to be the algebra till n. Okay, let's say it depends on the rule. And like A is the algebra from 0 to n plus 1. Here we get exactly the classical Markov property, but in a more sophisticated way, because here we see that the expectation E, I mean, the transition expectation E, maps A n plus 1 into an. Therefore, it exactly describes the transition, I mean, the dependence of the future upon the present given the past and the present. Okay. Now, this transition expectation allows to describe a satisfactory quantum extension of Markov chains, which was introduced by Luigi Accardi in his PhD thesis in 1974. Again, here is correct. And the quantum Markov chain is defined to be a triple phi 0 En and Hn, where phi 0 is a state on the algebra A0. It replaced the initial distribution of x0 in the classical case. And a sequence of transition expectation, because before it turns out that it's sufficient to consider En, since the transition expectation can be described as a identity tensor E for a transition expectation. Here we have the transition probabilities from the present and the future to the present. And then the boundary condition, Hn, which is an extra condition. However, it exists in the classical case, even for the Gibbs measures, which allows to study of phenomena of phase transition for classical Gibbs measures and like Markov in general. Here also, it serves a lot for quantum Markov chains on trees to define like phase transitions and many other interesting properties. Now, a Markov chain is defined to be a state. As we see, the classical Markov chain turns out that it can be summarized to be a state also in the commutative algebra, as we have seen before. Now, it should satisfy this condition. The finite correlations are given by this by this expectation. By 0 is 0, A0 of this composition. Okay. Now, since we have this definition of Markov chain, which has been proven to be applied in several domains, including physics, also bioinformatics and biology and so on, it's rather important to suggest a quantum extension of Heda Markov model, which is based on this definition, not on like some other theories, because as we can see that the classical Heda Markov model is based principally on Markov chain. Therefore, it's interesting that the quantum extension is also based on the quantum extension of Markov chain. Okay, in the literature, there are some other approaches to define the, I mean, 2 or 3 approaches only to define a quantum extension of Heda Markov model. One is given by a physicist, and the purpose is to study open quantum systems, and it is defined in terms of quantum operations. One other is defined in terms of also quantum channel, but it's both of us, they are considered to be like quantum information extension of classical Heda Markov model, but a probabilistic extension is not done. That's why we investigate it in this paper. I mean, indeed, it was a paper. Now it becomes like 3 papers, which are submitted to Jacobi, and one is published already. Okay. I mean, before the invitation of Rafiq, it was 1 paper. Okay, the transition expectation include like all the information of the transition of the process from AN, tensor AN plus 1 to AN. And here we can see that we can define 2 Markov operators, the forward and the backward one. The forward one is acting on the first component on AN, so it maps AN into itself. And the backward one acts on the second component, which maps AN plus 1 into AN. And here what's really interesting is that in the classical case, in the commutative case, this map is simply reduced to F times P backward. I mean, we are here in L infinity, so the times is the point by point product. One can see that the information on En is summarized by P backward here, by the backward Markov operator. What is really interesting, like, is that in the classical case, now we are in L infinity, okay, of S. So things are commutative. The product is the point by point one. We can see that if we take F is the identity, all the information is summarized by the backward Markov operator. While in the quantum case, it's not true, because it turns out that both the Markov, the classic, I mean, we cannot reconstruct E is not, let's say, it's not generated by P backward and P forward. It's much more complicated. We cannot get the transition expectation En if we know the information is summarized by P backward and P forward. Therefore, it's like similar to when you have a joint distribution of a couple of random variables, Xn. If you know the marginal distribution of P on the first component and the second one, you cannot get the full distribution because you don't know the dependency between X and Y. So it's also generalized the notion of dependence and independence. Because if we can construct En starting from P backward and P forward, it becomes trivial. So it's in some sense the tensor product of these 2 Markov operators. Therefore, it's a quite interesting notion, and it allows to give a really non-trivial extension of Markov properties. Okay. Now we are ready to define the hidden quantum Markov process, and everything is ready because we just need to replace the space L infinity of SH and SO by arbitrary C-star algebra over Hilbert spaces H HN and HON, which are here, let's say finite dimensional or separable, doesn't matter. And like you replace the tensor product, I mean, the operator, I mean, the emission operator, PHO, to be a general transition expectation in the sense I explained, in the sense of Markov chain. And to be a general transition expectation from AHN tensor A to N to AHN. So it maps AHN tensor at the same time. As you see, means that the observation at time N depends only on the hidden time N. Also, we need to replace the transition of Markov chain by the transition expectation EHN from AHN tensor AHN plus 1 till AHN for the hidden. Here we just add HN and ON to distinguish between the hidden process and the observation process. And now we are ready to define the non-commutative simple algebra to be AHO is the tensor product of general system algebra rather than L infinity of H and L infinity of SO. And like the global emission operator is defined to be the tensor product of these operators, which shows the independence the time, because it shows that at time N, it depends only on I mean, the observation depends only on the hidden. By the way, the dependence on the quantum case means the tensor product. It means that, I mean, even in the classical case. Now we get these results that describe the correlation of Hidden-Mark model to be defined as a state, which, as you can see, contains two components. One is the correlations of the Markov chain as described by these maps, which are EHK. Here is the Markov chain, the hidden, I mean the quantum Markov chain, controlling the Hidden-Mark, the quantum Hidden-Mark model. And like here are the emission one, involves also the observation. So we can see that it's like an extension of the classical case, but with the more sophisticated structure. Now we are ready to give the definition of what is called hidden quantum Markov model to be a state equivalently a triple as the triple of the classical one. Phi 0 is the initial state, E is the transition of Markov chain, and here is the emission operator of the observation given. We may also add the boundary condition. This will be done later to study the phenomena of phase transition, because it's all the time possible to add the boundary condition. Okay. Okay, now the information at time N is encoded by this map, which contains both the hidden and the emission operator. It's encoded information at time N. Now we are like, of course, if we make an extension, it should be related to the original problem, which is classical probability. Therefore, since we said that it's a non-commutative extension, therefore it's quite natural to forecast that when we restrict the process to the diagonal algebra, it should be a classical hidden Markov model in the usual sense. That's why we considered the hidden process associated with diagonalizable Markov chain. And we need these assumptions. Basically, we take the same algebra to be B of H both for the observation and the hidden are both isomorphic to a single algebra. And also, I mean, star isomorphic, of course. And we suppose that all the transitions are homogeneous here only for simplicity, because things are a little complicated. Therefore, it's rather better to consider the homogeneous case. But even like the inhomogeneous case can be treated in future work. And like we consider the usual expression, which is quite useful in physics, to be using faster trace. Basically, there is representation of completely positive map. Here is one of them. We use the partial trace of the second component, and like partial trace is defined to be, defined to be a linear extension of this map it kills simply the second component by tracing it and let the first one. Therefore, it maps B tensor B to B. And now this third assumption is that we assume that the conditional density amplitude is like it computes with the shift. I mean, with the first initial state here by zero, it commutes. It's not the full commutativity because it's only commute because let's clarify the picture. Here, K it belongs to the algebra B tensor B. Okay, and W0 it belongs to when we say that W0 tensor 1 commute with K, it does not mean that they commute everywhere. I mean, all the time. It may happen that one tensor W0 does not commute with K. Depends on the structure of the first component and the second component of K. Therefore, this commutativity is a partial commutativity, which is required here to be able, like, to define the. Okay, and like we assume that omega 0 is diagonal, it's natural to consider the diagonal less symmetric because we are interested in the diagonal restriction. And now we take the usual simple algebra, we reproduce them in terms of tensor embedding. It means that they are copies of the same algebra because we take the homogeneous case. All of them are copies of the same algebra. And now we are ready to consider this diagonal algebra, which is simply the tensor product of the diagonal algebra with respect to a fixed basis of the hidden or observation also Hilbert space, because we say B is B of H. Here we can take different bases, a base for the hidden and a basis for the for the observation. Okay. Now we have this technical lemma, which shows that under the three above assumptions, the conditional density amplitude K should be in this form, where P is indeed a stochastic matrix. Therefore, the classical case appears automatically when we restrict the study to the diagonal subalgebra. It appears in the conditional density amplitude by any square root of a stochastic matrix.
So, Dr. Souissi, you have also 5 minutes. So you can resume the rest.
5 minutes.
Yeah.
Okay. Here is like a result that we've obtained by restricting the Markov model to the O algebra, and it gives the classical Markov model. It's like distribution quite similar to the classical Markov model that we have seen in the first, and that we have this conditional probability depend upon these wave functions, which are the square. The inner product of EM and AO, which are quantum objects. And now we are ready to the last part. Indeed, this part was published with Souissi, in last year. And now, similarly to the entangled Markov chain, we can define the entangled Markov model using this Markov operator, which is entangled. I mean, it involves the maximally entangled vector associated with the an orthogonal matrices, and then we define everything this way, like in a very clear way, and we get also a result concerning the correlation of this process. Like it involves basically the Schur multiplication, the Schur product, two matrices, and the tensor product. Here it uses usual matrices. Okay. And now, what is interesting is that this transition expectation is diagonal preserved. It maps the diagonal algebra with respect to the fixed basis, tensor itself into itself. And now we define this Hedmark model having this transition for which the hidden transition expectation is entangled to be entangled Hedmark. Okay, recently there is also work on the bi-entangled one, which consider both the hidden on observation and the emission operator, both of them are entangled. And now we also can, okay, here is the result you obtained about the correlations of these Hedmark models, I mean, these entangled Hedmark models. And also we can recover Hedmark model as well from the entangled one. Okay, by considering KHO in this way, and we get the diagonal restriction of this process 41. If we consider its diagonal restriction, we get exactly the classical Hedmark model, but written in an algebraic way. Here, they are diagonal coefficients that they can be considered to be maps. Here, okay, the element A in which we apply phi 0 is simply a diagonal, A11, A22 till ANN. So it can be it can be considered as a map from L infinity of 1 till D to C. Therefore, it's the same for B. Okay, maybe. Okay, I just want to finish by giving some upper problems related to this work. First, it's quite important to consider the ergodic properties of the Markov model, such as the mixing, the clustering, and the asymptotic factorization of these processes. Nothing is done in this direction. Also, a quantum version, I mean, a satisfactory quantum version of the Viterbi algorithm. It's known that the Viterbi algorithm plays a crucial role in natural language processing, in classical natural language processing, I mean, machine learning. Therefore, it's quite interesting that a quantum version could also play a crucial role in this direction. Now, there is also the quantum natural language processing, but it's rather through another approach, what is called the quantum pictorialism. So I think it's really promising this direction. Also, the hidden quantum Markov model, quantum Markov fields, which is one of the hardest problems to be investigated. Concerning first, we should find a satisfactory extension of quantum Markov fields as a no-committed extension of the de Bruijn Markov field. The de Bruijn Markov field for which we have the conditional from inside to outside, not, I mean, with respect to finite regions. I mean, from finite region to the complementary. So it's rather a statistical physics conditioning, not probabilistic. Here, if we find the quantum Markov field, therefore, it's possible to associate a Hedmark fold structure in the quantum space. Also, we can investigate phenomena of phase transition for the quantum Heisenberg model and the quantum open quantum works and many other works, such as what is called the alpha random walk, but even alpha have been studied many years ago in biology, and it was not even called alpha random walk, but it was just a process with some application in biology. Also, we can investigate the hidden Markovian process. And I mean, in this section also, we can involve the step or process of alpha random walk, not the process itself, because it's Markovian. I saw some presentation in the applied mathematics webinar about alpha random walk, and here it can be investigated only the step one to give an example of non-Markovian dynamics. Okay, maybe that's all. Thank you. I give just some references. I just reduced the references to the paper used in this presentation, but many other references are needed to have a clear idea about the subject. Okay, thank you.
So thank you so much, Dr. Abdessatar. Any question, please?
Yes, please, Dr. Mohammed. Thank you very much for this nice talk, Dr. Abdessatar, in this very sophisticated area of research. A remark just for the public, as you have remarked, that at the end of the talk, our speakers has some open problems, some open questions. In general, the specificity of our webinar that we have very generous speakers that they are very open to collaborate and to discuss. If any of one from the public is interested by one of these questions, he can write to Dr. Abdessatar and he can discuss with him. He is very open to collaborate. I have some general questions, not very specific questions, but general. The first question, why quantum Markov chain? In other words, have you some applications of quantum? What is the extra of quantum Markov chain if we compare with classical Markov chains?
Okay, thank you for this next question, because it's quite natural to ask this question. Why we just generalize things to algebra? Because I see some mathematical theories, you just generalize things with no and. But quantum Markov chains have been proven to be applied in basically in physics in a series of papers by I think Bruno, Gale, and Werner, Bruno, and Slager, and so on. They published a paper in which they proved that the valence bound state of some physical interesting state are indeed what is called finitely correlated states, and these finitely correlated states are exactly Markov chains. And even it is forecasting that these states can be connected with this notion. I mean, they can be described in a more appropriate way using hidden quantum Markov. Also, there are some other biological applications of basically not only biological but psychological as well. Papers published by Krinikov. He published many papers about the Markov-like model, the quantum Markov-like models for brain and for psychology, for many domains. And another important application is in quantum information itself, because if you can see, quantum information is based on some notions like quantum operation or also a quantum channel. But if we focus little in some line, we can prove that quantum channel is indeed the dual Markov operator. Therefore, in the literature, Markov operator has been discovered a long time ago, but quantum channel, they are recent notions. So sometimes, like even you may use the notion without like even changing the name and so on, but it's proven to be applied in many domains.
Thank you.
I hope I give a satisfactory. Otherwise, I can send some references as well.
Okay, thank you. Another question. Can you give more details about the info on the work on quantum Markov chain? The area of quantum Markov chain. What is the relation?
Yes. Okay. Okay. The random walk. Actually, we just start to do some entangled extension of the alpha random walk, because what is called alpha random walk has been like studied many years ago, in the 80s and even before, by Accardi himself and his colleagues, to even as another application of quantum Markov chains in to detect protein, and like it was useful, but it was not colored in infrared mode. Infrared mode was discovered by the physicist. I mean, not discovered, but reformulated, and mistakenly he stated that it's non-Markovian dynamics. But then it turns out that it's Markovian, but non-homogeneous. But what is non-Markovian in the infrared mode is the step process, because the elephant, remember, random step, and then like I will try to write some details. And the step process sigma n is like actually, if I find the paper on which we make the calculation, it will be better. But here, if we consider this step sigma n, they are the step of the elephant. I mean, similarly, they are either 1 or -1. It's like a Bernoulli negative. And like, I mean, and also we can take xn to be the sum of sigma. And the sigma n is like randomly, it's like uniformly distributed over, let's write things in, how to say, in sigma 0 till sigma n -1. So it's defined through a conditional expectation over, therefore, this is not Markovian because it depends on sigma 0 till sigma n. It choose like the elephant one at time and it choose a random step. I mean, if for example he just take a right step in the first, then I don't know, a left step and so on. Like I mean, sigma n he took randomly, uniformly on the past steps and like take that step. So it depends on all the past.
Okay.
But the process itself is not is Markovian, but its inhomogeneity is also important. What we have done is exactly the analog, I mean, of this. Till now, we did like we take the transition of the elephant random walk, the correlation function, and we define a process similar to this one using these transitions. Right now, we are interested in the ergodic behavior of elephant random walk. We will see rather whether it satisfies some mixing property or not. That you are doing now.
Okay. Okay. Thank you. Thank you again.
So thank you. Any question, please?
Yes, there are a question.
Thank you, sir, for your presentation. I just wanted to know, like, for the demonstration for the ergodic property, like, is it in the same state as, like, in the paper that proves the hidden Markov sources are ergodic? Like, the characterization, is it like the same case, or would it be restrained? Like,
Actually,
that's my question.
but it depends on what's the property you want to show, because there are several ergodic properties. There are mixing, time mixing, ergodic, asymptotic factorization. But basically, we have done these properties for a class of Markov chains.
Okay.
Naturally, we will try to extend this notion to the. I mean, basically, we will try to see whether, because these notion have been illustrated in quantum Markov chains for some specific assumptions. We will see whether the observation process influence these. I mean, are they stable under the influence of the emission operator? That's
So
the first step.
Is there a chance it could be like topologically mixing, like with regards, like just mimicking the same demonstration that was like in the normal state? It could be, we could reproduce that in the quantum hidden process.
But okay, I don't know. But what do you mean by topological?
Like say for a process to be chaotic, you have three, like the Devani chaos definition.
I
Like
don't have any
you
idea
have,
about this. I'm sorry, because maybe if I have the definition, I will try. But
okay.
I don't know. I don't
Could
know.
you just provide any
number.
email where I could like just send you this paper and ask you if that's possible?
Okay. Okay, of course. I will write my email.
Thank you so much.
In the chat right now.
If you can write also your email, the beginning of your slides, which will be published in the homepage of our webinar. We ask.
Okay, I will send like. I will send it by email.
Yes. Okay, with the email. Okay. We ask you also if there are related research articles link.
Yes,
So
yes, exactly.
okay,
I will send like some papers and with references.
okay, you put them in at the end of the slides, please. I think that there
At the
are
end of the system. Okay.
okay, okay.
Yes, question, please. So, thank you very much, Dr. Abdessatar, and see you in the next.
Thank you. Thank you very much.
I have a question.
For everybody. Yes.
Yes, you're welcome.
Thank you, Dr. Abdessatar, for this talk. I ask if this notion exists in time continuous.
I see.
It
Yes, that's quite
exists.
interesting. Iskandar, right now we just investigate the first like examples. I mean, the first formulation of hidden Markov model. So it's rather natural to start with the discrete. Right now there is nothing in this direction. Only the mere definition and the correlation, and also some bridges with the classical case. I mean, in the discrete case, nothing is done in the continuous case, and this is one of the problems that will be addressed in the future.
Okay, there is no work about if you take Markov chain in time continuous, there is no hidden quantum Markov, the notion of hidden quantum Markov.
Yeah, I think if it will be just, I mean, the translation to the continuous time, it's rather useless. Because as you define a notion of conditional expectation in discrete case for discrete sigma algebra, and then they translate it to the continuous time. Okay, it's good, can be publishable, but if you investigate them in connection with some interesting processes, like for example the Wiener process, if some people are like working in that direction, some expert, it's gonna be much interesting because it's indeed Markovian, like time continuous one. I mean, we should like apply this to a significant physical problem that requires time continuous dynamics.
And to give a relation with the quantum Markov semigroup.
Exactly, that's one of, I think you are working in that direction, therefore it may be interesting to investigate the hidden Markov model associated with the semigroup.